Have you ever wondered if the intelligence you interact with every day is merely a sophisticated mirror, reflecting your own expectations back at you? We stand at a crossroads where the most famous artificial intelligence systems in the world, machines we thought were approaching human brilliance, have just hit a wall. A new test has emerged, one that does not care about fancy prose or rhyming poetry, and it has left the giants of the industry scoring near zero. If you want to understand why everything you know about AI is about to change, and how a new breed of slow-thinking machines is rising to take its place, then stay with us. Before we dive into the heart of this digital revolution, please take a moment to subscribe to the channel and turn on notifications so you never miss a deep dive into the future. For years, we have been told that large language models are the pinnacle of human achievement, capable of passing bar exams and writing complex code. Yet, when faced with the ARC-AGI benchmark, a test designed to measure genuine reasoning and the ability to learn new concepts on the fly, these models failed miserably. This benchmark is not about memorizing the internet, but about solving simple visual puzzles that a human child could master in seconds. The failure was not a minor glitch, but a total collapse that exposed a deep, structural flaw beneath the polished surface of modern AI. It suggests that while our machines have become world-class mimics, they are still fundamentally missing the spark of actual comprehension. This revelation challenges the core narrative of the tech industry, forcing us to ask if we have been building faster horses when what we really needed was an engine. The models we use today are essentially statistical engines, predicting the next most likely word in a sequence based on trillions of examples. They are incredible at identifying patterns, but they do not understand the rules that create those patterns, leading to a profound sense of hollow intelligence. As we peel back the layers of this failure, we begin to see that the path to true artificial general intelligence requires a radical departure from everything we have built so far. It is time to look past the hype and examine the illusion that has captivated the world for the last several years. The illusion of intelligence in large language models is perhaps the greatest magic trick of the 21st century. These systems excel at surface-level fluency, speaking with an authority that masks a complete lack of grounded meaning. When you ask an AI a question, it is not thinking about the answer in the way you or I would, but rather navigating a vast multidimensional map of word associations. It is a process of sophisticated guessing, where the machine chooses the most probable next token based on the context of the billions of sentences it has read. This creates a convincing facade of understanding, but it is an understanding built on sand, lacking any connection to the physical or logical world. We often mistake this fluency for reason, but the two are entirely different animals. A model can explain the laws of thermodynamics perfectly because it has seen those explanations thousands of times. Yet it might fail to apply those same laws to a novel problem it hasn't encountered in its training data. This is because these models collapse when they are forced to step outside the boundaries of their memorized structures. They are essentially stochastic parrots, repeating the wisdom of humanity without ever truly grasping the why behind the words. This fundamental weakness is why an AI can write a beautiful poem about a sunset, but cannot tell you why the sun won't rise in the west tomorrow. The problem becomes even more apparent when we look at how these models handle the concept of time and state. In a simple story, a human can easily keep track of where an object is, who is holding it, and how its position changes as the narrative progresses. If I tell you that Alice put an apple in a box, moved the box to the kitchen, and then took the apple out, you have a mental map of that apple's journey. Current AI models, however, often lose the thread of these evolving variables because they do not have a persistent internal model of the world. They see the words, but they do not see the state of the objects those words describe, leading to logical errors that seem baffling to a human observer. This struggle with context shifts and cause-and-effect relationships reveals a structural limitation in the architecture of modern transformers. Because the models process information in a mostly linear statistical fashion, they find it difficult to maintain a consistent truth when things change over time. They are stuck in a perpetual now, where every word is a new prediction, rather than a step in a coherent logical journey. This is why, in complex coding tasks or long-form reasoning, the AI might suddenly contradict itself or forget a crucial constraint mentioned only a few sentences prior. It is not just a memory issue, but a failure to understand that the world is a dynamic place where actions have consequences. To understand why this happens, we have to look at the technical core of the issue, specifically something called positional encoding. In traditional attention mechanisms, the model treats the position of words in a sentence somewhat mechanically, using mathematical coordinates to keep track of where each word sits. However, this method often ignores the semantic journey between ideas, treating the distance between two words as a simple numerical value rather than a logical bridge. This rigid structure is one of the primary reasons why large language models fail at logic-heavy tasks, such as executing complex code in their heads or following intricate conditional reasoning. They are essentially reading a map without understanding the terrain, seeing the coordinates of the destination but not the obstacles in the way. When a model encounters a problem that requires multiple steps of deduction, its mechanical approach to word positions becomes a liability. It tries to leap to the answer using pattern recognition instead of walking through the logical steps required to get there. This is like trying to solve a high-level math problem by guessing the result based on how the symbols look, rather than performing the actual calculations. Without a way to semantically link the evolution of an idea through time, the model remains a prisoner of its own architecture, unable to perform the kind of deep thinking that characterizes human intelligence. The limits of this approach are now becoming the primary bottleneck for the entire field of artificial intelligence. But just as we began to recognize these limits, a new class of AI entered the scene: the large reasoning models, or LRMs. Unlike the instant response models we are used to, these new systems are designed to slow down and compute during the problem-solving process. They do not simply spit out the first statistically likely answer that comes to mind, but instead engage in a period of internal deliberation. This marks a massive shift from reactive output to active reasoning, moving away from the fast-thinking intuition of traditional models toward a slow-thinking, analytical approach. It is the difference between a person giving a gut reaction and a scientist carefully working through an experiment. This new paradigm is exemplified by models like OpenAI's O1 series, which are trained to use a chain of thought before delivering a final response. When you ask these models a difficult question, they spend seconds or even minutes exploring different solution paths in the background. They are essentially talking to themselves, testing hypotheses, correcting their own mistakes, and validating their outcomes before the user ever sees a word. This deliberate calculation allows them to tackle problems that were previously impossible for AI, such as high-level mathematics, complex logic puzzles, and intricate programming challenges. They are no longer just guessing the next word. They are building a bridge of logic to the correct conclusion. The difference can be best understood through the lens of a chess game. A traditional large language model plays chess like a beginner who has memorized a few common openings and patterns but doesn't actually understand the strategy. It might make a few good moves by chance, but it will eventually stumble because it cannot look several turns ahead. An LRM, on the other hand, plays like a grandmaster who calculates multiple variations and anticipates the opponent's responses. It doesn't just recognize the pattern of the board. It calculates the path to victory, weighing the risks and rewards of every possible move. This shift from pattern recognition to deliberate calculation is the most significant breakthrough in AI since the invention of the transformer itself. We are already seeing the concrete achievements of these new models in fields that require extreme precision. Advanced reasoning models are now dominating elite benchmarks in science and mathematics, solving problems that were once thought to be the exclusive domain of human experts. They can handle massive context windows without losing the logical thread, allowing them to analyze entire libraries of technical documentation or tens of thousands of lines of code. Even open-source players are emerging as serious contenders, proving that the ability to reason is not just a secret weapon for the tech giants but a new standard for the entire industry. The results are undeniable. When the stakes are high and the logic is complex, thinking slow is the only way forward. One of the most exciting developments in this area is MIT's concept of path-based logic, which reframes how models understand relationships between ideas. Instead of just looking at the distance between words, this approach focuses on the journey of logic that connects them. It treats meaning as a series of semantic paths, where the model must navigate from a premise to a conclusion through a valid sequence of inferences. This signals a deeper move towards semantic awareness, where the machine is conscious of the logical structure it is building. By prioritizing the path over the pattern, researchers are creating systems that are far more robust and less prone to the hallucinations that plague current models. This move toward path-based attention is essentially an attempt to give AI a mental map of logic. Imagine trying to find your way through a new city without a map Relying only on the visual similarity of the streets, you would eventually get lost. But if you have a map and understand the underlying layout, you can reach your destination even if the surroundings change. Path-based logic provides that map, allowing the model to navigate complex problems with a level of certainty that was previously unattainable. This transition from word guessing to logical pathfinding is what will ultimately define the next decade of artificial intelligence development. However, this newfound intelligence comes with a significant catch. The real-world cost of reasoning is hitting the industry hard. Reasoning models are extremely expensive to run, as they require massive amounts of computational power to sustain their internal thinking processes. While a standard query might cost a fraction of a cent, a deep reasoning task can sometimes cost hundreds of dollars for a single answer. This creates a massive financial barrier for individual users and small businesses, turning high-level intelligence into a premium commodity. Organizations are now forced to weigh the cost of a golden answer against the speed and efficiency of cheaper, less accurate models. Despite these costs, many organizations are finding that the precision of reasoning models dramatically outweighs the volume of traditional output when the consequences matter. In fields like medicine law and structural engineering, a single mistake can be catastrophic, making the investment in a slow-thinking AI a strategic necessity. If an AI can spend $500 to correctly diagnose a rare disease that a human doctor might miss, that cost is easily justified. We are moving toward a world where intelligence is no longer seen as a cheap, infinite resource, but as a graduated service where you pay for the level of thought you require. As a result, the market is beginning to optimize, searching for a balance between cost, speed, and accuracy. We are seeing the rise of distilled reasoning models that attempt to pack the logic of a giant system into a smaller, more efficient package. Enterprises are rethinking their entire infrastructure to reduce dependency on the most expensive systems, using them only for the most critical heavy lifting, while leaving everyday tasks to smaller models. Intelligence is becoming a strategic investment, a tool that must be managed and deployed with care rather than a commodity that is sprayed at every problem. This shift in economic reality is forcing a more mature and disciplined approach to AI adoption across the globe. Yet, despite this incredible progress, the narrative must eventually pull back the curtain on the harsh limits that still stand. If we look at the most difficult reasoning benchmarks, even the most advanced AI still performs poorly compared to a well-trained human mind. Speed remains a significant bottleneck, as the time required for a model to think can make it impractical for real-time applications. Furthermore, the usability of these models suffers when they take minutes to respond to a simple prompt, creating a friction that many users find frustrating. We must accept that scaling alone, simply throwing more data and more chips at the problem, is no longer enough to bridge the gap. The industry consensus is shifting away from the bigger is better philosophy that dominated the last few years. Researchers and leaders at major AI conferences now agree that we have hit a point of diminishing returns with simple parameter scaling. The next leap in artificial intelligence will not come from a bigger dataset, but from a conceptual innovation that changes how these systems fundamentally operate. We are looking for the new physics of AI, a breakthrough that allows for human-level reasoning without the astronomical energy and financial costs of our current methods. The era of brute force intelligence is coming to an end, making way for an era of elegant, structural innovation. This is where hope returns at the fascinating intersection of multiple scientific disciplines. By merging the intuition of neural networks with the logic of symbolic AI, researchers are aiming to build systems that can both reason and generalize like humans. These neuro-symbolic models aim to combine the best of both worlds, the fluid, pattern-matching capabilities of LLMs and the rigid rule-based logic of classical computer science. Experimental ideas that were once considered fringe or outdated are now moving to the center of the conversation. This hybrid approach could finally give us a machine that doesn't just simulate intelligence, but actually possesses the structural framework for it. At the same time, hardware evolution is accelerating this transition to a new era. The physical limits of traditional silicon chips are being challenged by next-generation hardware designed specifically for the thinking phase of AI. We are seeing the emergence of quantum classical hybrids and ultra-efficient servers that can process the complex chains of thought of LRMs with a fraction of the energy. These chips are being built not just to move data faster, but to facilitate the deep, interconnected calculations required for reasoning. As the hardware becomes more specialized, the cost of thought will eventually begin to fall, making advanced intelligence accessible to a much broader range of people. This evolution reframes the entire AI paradigm, shifting our focus from predicting words to predicting meaning. The future of artificial intelligence is not about guessing which letter comes after A, but about anticipating the next logical inference, the next decision, or the next creative breakthrough. This distinction defines the new era we are entering, one where the intelligence in AI actually stands for something substantial. We are building machines that can navigate the vast space of human ideas with a sense of purpose and direction, rather than just drifting on the currents of statistical probability. This is the transition from a digital librarian to a digital philosopher. It is important to conclude without the usual hype, recognizing that these reasoning models do not replace the large language models of today. Instead, they complement them, creating a diverse ecosystem of tools for different needs. The fast models will continue to handle our everyday tasks, like writing emails or summarizing documents, where speed is more important than deep logic. Meanwhile, the slow thinkers will be reserved for the hardest problems, the ones that require deliberation, accuracy, and a deep understanding of cause and effect. Together, these two types of systems expand the horizon of what AI can achieve, giving us a complete toolkit for the digital age. The real transformation, however, does not lie in the models themselves, but in what we as humans choose to build with them. We are now in possession of two distinct types of digital brains, one that is intuitive and one that is analytical. The open question that remains is how we will integrate these tools into our lives, our work, and our society. Will we use them to solve the world's most pressing problems, from climate change to disease, or will we let them become another source of noise and distraction? The choice is ours, and the responsibility is greater than it has ever been as we step into this new era of reasoned intelligence. As I look at this landscape, the lesson I take away is that true intelligence is never about having all the answers instantly. It is about the willingness to slow down and ask the right questions. In our own lives, we often rush to judgment, relying on our fast intuition when a slow deliberation is what the situation truly requires. My advice to you is to embrace your own reasoning mode more often, especially when the consequences of your decisions matter most. In a world that is moving faster than ever, the ability to stop, think, and deliberate is the ultimate competitive advantage. It is the very thing that makes us human, and now it is the very thing we are trying to teach our machines. Before you go, I want to ask you a question. If you had access to an intelligence that was 1,000 times smarter than any human, but it took a whole day to give you one answer, what would you ask it? Please share your thoughts in the comments below, as I would love to see where your curiosity leads you. Thank you for spending this time with us to explore the frontiers of the mind and the machine. Don't forget to subscribe to the channel for more deep dives into the future of technology, and I will see you in the next one.